Up until the latter half of the 19th century, there were two predominant theories about the fundamental structure of matter. The first and most popular of the two was one supported heavily by John Dalton, that atoms were solid, indivisible spheres. The second and slightly less popular theory was that matter was fundamentally continuous, and that atoms were either a mathematical convenience or elusive vortices in the ether that would always be too small to detect or measure. In 1897, J.J. Thomson tried to determine the internal components of the atom with the aid of a cathode ray tube. Thomson applied high voltages to electrodes in a vacuum, and when he activated the electrical field, a glowing beam shot across the glass. Thomson tried to calculate the mass-to-charge ratio of the particles making up this mysterious beam, while taking into account the deflection of the rays by magnetic fields. Thomson discovered these particles were thousands of times lighter than the atom itself, and therefore concluded that atoms are not indivisible but contain negatively charged corpuscles. He introduced his famous plum pudding model without identifying exactly how the rest of the atom was structured, leaving the exact nature of the positive charge a mystery. This debate over atomic structure would rage on for around another decade. But the first true evidence of atoms having a dense, centralized core would come in 1909, when a brilliant physicist would have a burst of intuition that would lead to the discovery of the atomic nucleus. Ernest Rutherford was born in Brightwater, New Zealand in 1871. Little is known about Rutherford's early life other than the fact that he enrolled in Canterbury College in 1890 at 19 years old. His mentor later at Cambridge was J.J. Thomson himself, the physicist who discovered the electron. In fact, Thomson made his key discovery just shortly after Rutherford began working in his laboratory. Rutherford, while at Cambridge, also had the job of studying newly discovered X-rays and radioactivity, and therefore he had the opportunity to learn advanced atomic physics directly from the world's leading experts. In 1907, Rutherford moved to Manchester to head the physics department at the Victoria University. He spent the next several years there, focusing specifically on radioactive emissions, particularly alpha particles. After making several years' worth of observations of these fast-moving particles, he noticed something peculiar about how they traveled. Rutherford had been using a zinc sulfide screen to measure the scattering of alpha particles passing through thin sheets of mica, and noticed that when the beam hit the matter, the flashes of light were slightly blurred, meaning the particles were being deflected by a couple of degrees. Rutherford could come to two main conclusions after observing this phenomenon. The first was that the electric fields inside atoms were relatively weak, causing only minor variations in the alpha particles' path as expected by the plum pudding model. The second was that there were intense, highly localized electric fields inside the atom capable of deflecting massive particles. To try and figure out which of the two possibilities was correct, Rutherford began studying the scattering of alpha particles as they passed through ultra-thin gold foil. Later on, Rutherford tasked his assistants to document the results, where he explained them using a simplified geometric diagram. When an alpha particle approaches the gold atoms, most pass straight through empty space. But when a particle comes dangerously close to the center of a gold atom, it interacts with an immense positive charge. The incoming particle would have to endure an incredibly strong repulsive force to be deflected. So, Rutherford just needed to calculate how many particles were observed rebounding at extreme angles, compared to what was predicted through Thomson's widely accepted model. Rutherford found this extreme deflection phenomenon to be exceedingly rare, about 1 in 8,000 particles bouncing completely backward. Combining this with the calculated velocity of the alpha particles at the time, which was done by his assistant Hans Geiger, and some additional complex geometry, Rutherford concluded that the entire positive charge of an atom is concentrated in a volume roughly 10,000 times smaller than the atom itself. This massive central core is what we now know as the nucleus. Most of the early skepticism of Rutherford's calculations was attributed to two correlated assumptions. The first was the calculated size of the electron's orbits, which turned out to be somewhat unstable under classical physics. The second was the exact mass of this newly proposed nucleus, which was initially too difficult to quantify perfectly. Rutherford published his groundbreaking results in a paper entitled The Scattering of Alpha and Beta Particles by Matter the next year, in 1911. About 2 years after Rutherford's work brought to light the first experimental evidence of the dense nucleus, English physicist Henry Moseley refined the understanding of it even further using an entirely different method, X-ray spectroscopy. Moseley's intention was not to calculate the size of the nucleus, but rather to find evidence of a fundamental physical quantity tying atoms together by measuring the X-ray spectra of different elements. Moseley figured that if he were to measure the shifting frequencies of X-rays emitted by different metals, it would further validate the theory that atoms are organized by a distinct nuclear charge. Rutherford himself also pondered this, but the alpha scattering angles were too imprecise to firmly establish exact atomic numbers. Moseley was indeed able to find a stunning mathematical relationship, uncovering a different phenomenon, a step-by-step shift in X-ray frequencies perfectly matching the sequence of elements. With some genius insight, Moseley determined that these precise spectral shifts were due to the increasing positive charge of the nucleus in a phenomenon now known as Moseley's law. When high-energy electrons strike a specific element, the X-rays emitted are inextricably linked to the number of positive protons residing in its core. The discovery of this mathematical law by Moseley not only provided the first direct evidence that the periodic table is ordered by nuclear charge rather than atomic weight, but also allowed him to identify missing elements in the table quite precisely. He determined that the atomic number is a physical reality, clearing up years of chemical confusion, and also determined that the nucleus contains a discrete, whole number of positive charges. The evidence provided by Moseley was crucial in determining that the nucleus is fundamentally structured. There was a lot of opposition to Rutherford's conclusions after his initial publication, led mainly by Thomson himself, who still believed that the plum pudding model was correct. He believed that these weird anomalies in alpha scattering were due to multiple minor collisions within the atom, and not because of a single dense core. Thomson had tried to model the atom's structure earlier in his career as well, and through different mathematical methods. But when he couldn't reconcile the instability of orbiting electrons, he adopted the diffused positive charge theory and held it for quite some time. Moseley provided further evidence that Rutherford was correct in his conclusions, and other physicists who came after Moseley further refined his results. In 1913, Danish physicist Niels Bohr used a combination of quantum theory and atomic spectra to further refine the orbital model of the atom. Up until this point, all of the detailed probes of the nucleus had been somewhat limited by the natural decay of radioactive elements. No one had yet successfully shattered a nucleus completely to isolate all of its hidden parts, for no one had a strong enough experimental apparatus, or if they did, they didn't have the technology to manifest that experiment into reality. Once the first theoretical models of the atomic nucleus were accepted, though, many scientists realized to what degree of fundamental forces they were working with regarding the core, and therefore realized the grand scale at which they needed to make an experimental apparatus. English physicist James Chadwick was among the first to successfully use such a dedicated setup, and subsequently discover the missing mass of the nucleus based off of tracking mysterious, uncharged radiation. Chadwick's 1932 setup went as follows. He used a specialized vacuum chamber with a polonium alpha source at one end. In front of this source, he placed a thin target of beryllium, and directly behind that, he placed a block of paraffin wax. He then began bombarding the beryllium so that a highly penetrating, neutral radiation would shoot out and strike the wax. The dislodged protons from the wax would be seen when they entered a specialized ionization chamber and reached the detector, and wouldn't be seen if the initial neutral radiation wasn't massive enough to knock them loose. Chadwick then began to analyze the energy of these ejected protons, calculating their momentum to prove that the mysterious radiation knocking them loose couldn't be massless gamma rays, which means that the observer was actually detecting a heavy, neutral particle. Then Chadwick used the known values for the mass of protons, the conservation of momentum, and the recoil velocities to calculate the mass of this new particle. His calculations yielded the existence of the neutron, solving the final missing puzzle piece of the atomic nucleus. Interestingly enough, at exactly the same time, a French physicist couple named Irene and Frédéric Joliot-Curie were independently devising a very similar apparatus, but with some slight differences in interpretation. The Joliot-Curie's setup also included polonium and paraffin, but in this case, the detection device wasn't an ionization chamber alone, but rather a cloud chamber. Radiation would travel from the beryllium source, hit the paraffin target, scatter the protons, and finally leave visible tracks for the observer. The cloud chamber allowed them to visually measure the energy of the ejected protons, observing them at a different trajectory relative to the source of radiation. Knowing the distances traveled by the tracks, the speed at which the protons moved, and the angle of ejection, the Joliot-Curies were able to calculate the energy of the event, which was extremely close to today's accepted nuclear mass values. The Joliot-Curies announced their results shortly before Chadwick, adding to the evidence pool of the complex nucleus and further refining its elusive true mass. Most of the measurements of the atomic nucleus up to this point have been close to accurate with minor errors, but they have not been all that precise. Most of the values round off to the nearest whole atomic mass unit. Filling in these decimal points would require much more precision. This technology would not come until the mid-20th century, and would come at the hands of an American physicist by the name of Ernest Lawrence. Ernest Lawrence is known more famously for his 1932 invention of the cyclotron, a revolutionary particle accelerator. It is the most famous atom-smashing machine in all of early modern physics, and provided strong evidence that the nucleus could be artificially split and precisely measured. The cyclotron itself operated through accelerating particles in a spiral path using high-frequency alternating voltages. Lawrence was a pioneer in precision instruments for measuring nuclear properties, and had been brainstorming ideas of how to refine nuclear bombardment since he was an associate professor in 1929. He started with trying to find ways to improve linear accelerators using better electromagnet technology, and expanding the energy at which the particles would travel during the experiments. In 1931, he would reach particle energies of 80,000 electron volts. While at Berkeley, Lawrence took mentorship and collaboration with Stanley Livingston. With better funding and a larger magnet, they refined their machine to push particles to over 1 million electron volts. Still, even with a more powerful machine, Lawrence was not satisfied. Several years after the initial cyclotrons, in 1939, Lawrence began planning a new massive experiment that would measure nuclear interactions from the Crocker Radiation Laboratory in Berkeley, California. Still using the same magnetic acceleration tactic employed years prior, and with the help of a massive 60-inch electromagnet weighing over 200 tons, Lawrence reached particle speeds of tens of millions of electron volts, allowing him to probe the nucleus with an error rate of mere fractions of a percent. This still was not the last attempt by the scientific community to refine the calculated properties of the nucleus further. There were some sources of error with these early accelerator experiments. The first was a relativistic mass increase that happened as particles approached the speed of light, which threw off the timing of the alternating voltage. This relativistic effect compromised the beam stability somewhat, and coupled with radiation leakage caused by the intense scattering of secondary particles, it's understandable that physicists were still not satisfied with their measurements. The next and final effort would continue for the rest of the 20th century and would evolve into monumental international collaborations. For these subsequent attempts, scientists invented a new and clever device, the synchrotron. This device was essentially a massive underground ring, sometimes kilometers across. Perhaps the most impressive aspect of this ring was not its size, but the fact that the entire beam pipe was made to be almost a perfect ultra-high vacuum. Physicists, frustrated with the atmospheric scattering affecting their measurements in the previous years, wanted rogue gas molecules to have absolutely no effect whatsoever on their next nuclear measurements. Inside the tube were a series of superconducting magnets that steered a particle source successively, millions of times a second. This setup was able to extend the particle's path inside the ring to effectively millions of kilometers, before it collided with a target and then went to the massive detectors to measure the angles of deflection. the scientific community planned a series of countless measurements throughout the course of several decades to get the most precise understanding they could. Unfortunately, though, Lawrence died in 1958 before the largest of these supercolliders were built. The mile-long rings were not immune to error either. Since many were built in geologically active areas or faced subtle terrestrial shifts, they were prone to microscopic misalignments, which would shift parts of the beamline at times. They were in constant need of maintenance due to that, and also due to immense cooling requirements affecting the superconducting magnets during their experiments. Regardless, the results from these machines brought about the standard model of particle physics, mapping the exact masses of protons and neutrons down to incredible precision. Since the early cyclotron calculations, the structure of the nucleus has been refined further to reveal quarks and gluons. It's astounding how well the initial scattering method worked, and how it was the primary method of calculations up until the modern era of gigantic particle colliders. Today, the mass and charge of the atomic nucleus are officially set as fundamental constants, and the definition of atomic mass is derived from these incredibly precise values. This means that today, measuring the nucleus does not just impact the accepted weight of elements, but rather further refines our understanding of quantum mechanics as more and more precise measurements are made. The atomic nucleus is incredibly dense relative to our macroscopic world, but compared to the scale of a whole atom, it is incredibly minuscule. It's the anchor of all visible matter, and unlocking its secrets is a prime example of pushing quantum physics to its limits. The sheer fact that scientists in the early 20th century were able to take what seemed indivisible to them before and turn it into a meticulously mapped structure is beyond remarkable. Thanks to a century's worth of innovation and the work of many brilliant physicists, our understanding of the nucleus has grown significantly, along with the fundamental limits that lie within our universe. Thank you for watching. This video is brought to you by the Deepstash app.